Hello, hello, and what's up to you all pre-matriculants? My name is Abram, and you're chilling together on this lovely physical sciences afternoon. I hope you're all pumped up and ready to learn more with us. I hope your day was cool at school and you enjoyed it. If you didn't, trust us to twist and turn your mood around and make sure that you learn more and learn extra. I'm not alone. I'm with John today. John, how's it?
Very good. Thanks, AB. Welcome, grade 11s. We're really into some exciting stuff this afternoon. It's all about shocking. Talking about shocking. Did you have a shocking experience today at school? Did you feel the ground move? Did you feel a little bit scared? Well, let us know. Post us, hit us up on Facebook, send us a tweet on Twitter. We'd love to hear your experience of that earth-moving experience. And talking about earth moving, let's have a look at the Facebook page because something has changed.
Something has moved.
Yeah, something has moved. So what you'll notice is the banner up at the top is quite different to what it was even yesterday because we've got some great things to announce. We're getting a campaign going called Get Connected. Abby, tell us about it.
Of course. Well, this Get Connected, remember my cities, it is adding up to the hashtag that we always use, that hashtag walk together. This is the journey, but now we want to connect with you guys. We want you guys to connect with our teachers and connect to our resources, and let's just connect with each other. But we've got cool prizes that are probably sponsored by Vodacom. Now, these are the instructions. Jump to our Facebook page to get all of these details. John has shown you our lovely Facebook look, where on top you can see we've got 4 Sony Xperia cell phones that we're giving away. They are up for grabs, guys, just for you guys. But we also have 6055 Rand airtime vouchers, proudly sponsored by Vodacom. Now, to win these airtime vouchers, all you need to do is to share the competition detail graphic on Facebook. John is going to show you that.
Okay, so guys, let's have a look. Here we go. There it is. Right pinned to the top are the steps that you need to go through. So what's the first step you need to get to? You need to register for this competition. And you need to register every 2 weeks. So from this week, for the rest of this week, if you enter once, that's it. Don't enter it. You won't be able to enter again for this week or for next week until next week, Thursday, until we announce the beginning of the episode for the next session, which will be in a week on Monday. Not this coming Monday, after that. So you register. You register at the link on Curio. Curio is a great platform because it means that you can answer the test yourself questions as well. So register there, get going, and the code for this competition isn't one of those strange ones that you've got to try and remember XYZ 32567. No, it's very simple. It's LEARN. It's LEARN. Capitals, lowercase, it doesn't matter. Register. On that wall, on the Curio wall, on the question, when you fill that in, you'll see a whole range of teachers. These are the teachers that teach week in and week out, starting on Monday through to Thursday, a selection of 6 of them. You've got to decide of these teachers who's your favorite. Okay. And what we've done is we've given them individual photos as well. Now, there's a photo of one of the teachers, and what we want you to do is vote for them on Curio, and then come and like the page, and like the teacher that you like. Tell your friends to like the page. Get your friends to vote for your favorite teacher as well. Okay? And when we do that, we will then use that the teacher with the most likes as that group of people will all go into the draw for the Xperia, the Sony Xperia. And we'll be getting the 2 most popular teachers from that situation. The links, if you can't find them, are on this post. If you just go see more, there are the links for all the teachers. In this round, we're dealing with Natasha, Tracy, Llewellyn, Camlin, Martin, and Wilson. So decide who you're going to vote for, enter, and then like the posts, like the pictures. The one that gets the most likes, that team is the winning team. Agree?
Nice one. I do agree, John. It's cool. It's It has got exciting news. So, guys, it's running for 6 weeks. So make sure that you enter.
But
almost
only these
every-
teachers are for 2 weeks, eh?
Yes.
Not for forever. So don't, I'll vote late. No, you
No,
take the
no.
chance now. And then, guys, there's one other thing. We also want to give away some airtime. So this is what we want you to do. We want you to take that graphic that is pinned to the top. Nobody, I can't see, has done it
You
yet.
need to
Ma-
refresh.
I might
You
need to refresh, eh?
yes.
And you need to share this whole story with your friends. Share it on your wall. Share it with a friend. Post it on their wall. Let's get everyone connected and taking this competition forward.
Well said. There's about 22 shares already. So, guys, the competition is heating up. So make sure that you share as many times as you can to maximize your chances of winning. But it doesn't end there. Let's get to learning now. The notes are on facebook.com/learnextra. There's the viewing and the download option. So, guys, get on them right now.
Okay, let's get on to some learning now. I know this other stuff is fun, and it is great fun, but I want to get into some electricity, talking about shocking stuff. We're going to start with some basics. Now, you started with basics of electricity way back in primary school, and you've built up, and you know a little bit about it from grade 10. We're going to do a bit of revision today, and then we're going to focus on applying our knowledge of this very important law, which you spoke about in grade 10, but you didn't really do the experiment or prove or talk in too much detail about, Ohm's law. So that's what we're going to do. So today we're going to look at those important definitions from the grade 10 work that you would have done, and we're going to talk about what is current, potential difference, and a new word, or what might be a new word, EMF. We're going to look at Ohm's law. We're going to identify resistors that are ohmic and those that are non-ohmic as well. And then we're going to apply Ohm's law to solve circuit problems where you have resistors in series and parallel. But let's get to the challenge question because that's calling us. So now it's not too straightforward, but it will challenge you a little. It has to be a challenging question. It says, use the circuit diagram to calculate the value of resistor R. Where's resistor R? There it is there. Okay? What it gives you is additional information. It says the ammeter in the circuit, not in this is the circuit, in the circuit below shows the same reading regardless of whether switch 1 or switch 2 are either both open or both closed. So you're going to have to work with that circuit diagram, recognize that if they're both open, the ammeter reading is the same as when they're both closed, and that's my hint for you. Go and work out what you think that resistor R's value is. Okay, now, what can we say about electricity? Where we usually start with the idea of a circuit. If you think about a circuit, you're going to need some energy, some stored energy. That stored energy comes from a series of cells that are connected together. They're usually connected together one after the other, and we say they're connected in series. When cells are connected together, they form a battery. That's the push. That's where the energy, the electrical energy, comes from the chemical reaction taking place inside of them. Can't be used unless you have a circuit that is closed, a pathway that is connected from one terminal to the other terminal. Must connect. When that happens, you get a movement of charge. So current is simply this. It's a movement of charge. And notice I'm just saying it's a movement of charge. I'm not saying positive. I'm not saying negative. In fact, what we think about in many situations is that there is charges of different sign move in opposite directions. So if positive charges move from the positive terminal to the negative terminal, at the same time, negative charges will move from the negative terminal to the positive terminal. This happens in an electrochemical cell, where inside the battery, it's making electricity, giving you the electrical energy. It produces for you those charges. only in wires, circuit wires, where the positive charges are held fixed in their metallic lattice do they not actually move. But they vibrate, and sometimes they vibrate a little bit faster, depending on the temperature. The point is that we can think about them as moving. The regions of positive charge in semiconductors, in things like silicon, in your phones, in your computers. You have these semiconductor materials where we have things called holes that move. And we think about them as being positive regions of space, charge moving. So guys, don't get confused. Charges move. They move at the same time. I like to think of positives moving one way, and in the opposite directions you're getting the negatives moving. So we've got to make it a choice about which way is this current going. We've got to make a choice. And again, scientists got together and they made a choice. They said, we're going to make a rule. And another name for a rule is a convention. A convention is a way of doing things. Convention, it could be either. We could say red is positive, black is negative. It doesn't matter. It doesn't matter to anybody, but we've made the rule. And the rule is, for the convention or rule, is that the direction of current, please notice, direction of current is the direction positive charges move. Charges would move. And which way is a positive charge going to move in a circuit? Well, it's going to go from the positive terminal of the battery, if that's a battery, and there's a resistor, and there's another resistor, and there's an ammeter, and we're going back. The long line is the positive line, the short line is the negative, and the direction of conventional current is from the positive terminal of the battery to the negative terminal, going through the full circuit. So once you've passed through this full circuit, you've completed the circuit. And that's the direction of current. Now, how do we measure current? From grade 10, you will have remembered, I is equal to Q divided by T. Now, the next thing that we need to talk about very quickly is potential difference. It's given a symbol V. It's measured in volts. And the symbol for volts is also V. Please don't get these mixed up. We recognize that V is the work done per unit charge. So it's the number of the amount of energy or work done, which is measured in joules, divided by the charge that is made to move between that, and that's measured in coulomb. Now, let me keep the notation correct, or the same. If I'm talking about work in coulombs, work in joules, then I must talk about charge in coulomb. So that will give us what 1 volt is. When 1 joule of work is done by 1 coulomb of charge, then we've got a potential difference of 1 volt. Last point is Ohm's law, and that's the focus of this lesson. We're going to say that Ohm's law is stated as this: the potential difference over a resistor is directly proportional to the current passing through the resistor, providing the temperature of the resistor remains the same. And so what we have here is the graph. And the graph might not have come out too clearly, so I'm just going to draw in the lines, the axis lines. And what we're going to see is if we have a line like that, then we will get a straight line, because the potential difference, V, let's just do that again, V against I is going to give us a straight line passing through the origin. So what are we going to say? That V is directly proportional to I. That's what the statement was. If we change this around into an equation, then we can say V is equal to a constant times I, which means that the constant is equal to V divided by I. And remember what that constant is. That constant is the gradient, this gradient. Now, what George Ohm did is he said, let's give this gradient a name. And he called it resistance. And for that, we now say this is resistance, and we measure it. The SI unit is an ohm. And that's the sum of the total of the story. Instead of now calling it a K, we change the K to an R, and we can say, there we go, that's Ohm's law. Now, the important thing is the constant. Temperature was constant. And there's one last thing. I'm just going to take 30 seconds to deal with it. Not all resistors act according to this graph. Those that do are called ohmic resistors, but some, when the temperature gets higher, their resistance increases. So the graph isn't a straight line, it becomes a curve. Things like filaments in old light bulbs, those are non-ohmic. Okay, AB, over to you.
Thank you so much. And well, my sisters, I see you guys on the page. Daniel, Mukove, welcome. Gift, welcome. Sanele, welcome, guys. I see you guys are on the page. Kulegani, thank you guys for joining us and enjoying the show. If you have some questions, feel free to throw them at me and John, and we'll make sure that we answer them. But remember, during this break, if I were you, I would start doing the test yourself questions in order for me to stand a chance of winning this awesome Casio calculator. So the links are already posted on facebook.com/LearnExtra. Also follow us on Twitter @LearnExtra. See you after the break. Welcome back, Minds. It is Prematrix. Now your challenge question is up and ready for you guys on the page. So better be starting now, and let's see if you get cracking it. If you're still stuck, make sure that you post those questions, and me and John are going to help you. But on the page also, there are great comments such as this one from Joel saying, yeah, the show is very great and the teacher is understandable. Shem, that's what we want, by Joel Mbata. Thank you so much, Joel.
Thanks, Joe. I'll give you something when I see you. Okay. So I hope you come and visit us sometime.
Nice.
Okay. Thank you, guys. Let's get going now with the questions. I want to remind you, though, we ran through that summary very quickly. There's a whole lot of information about differences between series and parallel circuits that are in the notes. Guys, get connected. Get the notes. Download the notes. The download note is if you can access a PDF file. The view note is if you're doing it on a mobile phone and you don't, that just takes you to a website and it just allows you to see the notes. You won't be able to save them and look at them, but you will be able to see them. Okay, so let's get the questions going and let's move on. The first question is a little bit of a warm-up question, and it really deals with concepts that were dealt with in grade 10. So let's get going with it. It tells us 120 joules of work is done when 15 coulombs of charge moves through a light bulb in 300 seconds. And what it asks us to do is calculate the potential difference across the light bulb. So we're going to say V is equal to W divided by Q. And I'm just going to work in one line because there's not much space here. 120 divided by 15. And if I'm not mistaken, the 15 needs to just be done again. But 15 into 120 goes 8 times. How do I know that? 30 goes into 124 times. And we can then work out that 15 goes into 30 twice. So 4 times 2 is 8. But you can check it on your calculator. Next one. What is the current? Now remember, current is I is equal to Q divided by T. It was 15 coulombs. Don't get confused. The time was 300 seconds. Now, I need my calculator for this one, so I'm going to make sure I've got it, and I'm going to say 15 divided by 300, not 30, 300 is a 20th, which is 0.05. So I'm going to write that in as 0.05 amps. Don't write AMP. It's A. It's the SI unit for current, the measurement of current. So please make sure you get it right. Next, what we're asked to do is to calculate the resistance of the light bulb. Now, you're all falling over yourself because you say, but we're doing Ohm's law. That's R is equal to V over I. We've calculated V. We said V was 8 volts. We said I was 0.05. And we're going to do that together. Now, here's a little trick that I really like on the calculator. Sometimes you work out a question like this and you've got the denominator as the answer on the calculator. And you could put it back in again and type it all over and clear the calculator. I prefer to do this. I find the 1 over x button. So now it's made it the denominator, and then I multiply by the numerator, which was 8, and I'm going to say the answer is 160 ohms. And there's our warm-up over. Let's move on to the second question. So let's read this question very carefully, because it may be a little bit tricky, or trickier than the one that we've done previously. So it tells us, let's pick out the key information, a battery of 4 1,5 volt cells. So just at the moment, I'm going to put 1,5 times 4, because that's the potential difference or voltage of the battery. And I'm just going to put it like that. An ammeter, so a battery, 4 cells, they're connected in series, it tells us later. An ammeter and 3 resistors, 2 ohm, 4 ohm, and 6 ohm, are connected in series to form a circuit. So what we need to do, first part of the question, is to draw the circuit. Now, when you're drawing a circuit, please be accurate. So that's one cell. The long side is the positive side. That's the second cell. That's the third cell. That's the fourth cell. So we've got our battery. It's connected to an ammeter. Ammeters are always connected in series. We also know connected in series to this is a resistor. There's a 2 ohm resistor. So we're going to do that one first. Call that resistor 1. Then there's a 4 ohm resistor. It doesn't matter that it turns the corner. 4 ohm. And then another one over here, which is the 6 ohm resistor. And there must be a complete circuit. So I'm just doing a freehand sketch here. You can use a ruler to make sure that you've got your points really nice and accurate. And there's no space left. It must be a closed circuit. So there's your resistor now. Or there's your circuit at least. Now it says to us, calculate the reading on the ammeter. The reading on the ammeter. What does an ammeter read? An ammeter connected in series reads the current passing through the circuit. When you're connecting an ammeter practically, you must always make sure that you know where the positive terminal is, where it's coming from the battery, the dimple on the battery, the little thing that sits out, that's the positive end. It's marked with a plus. That must go into the red terminal, which is marked with a plus on the ammeter. If you don't do that, you'll break the needle and you can damage the ammeter. The ammeter is a low resistance instrument, so it's very important that you not only connect it correctly, but you connect it to the highest scale first. So you would make sure that it doesn't get damaged. If the needle just moves, then you go to the lower scale, then to the lower scale still. So you would start like on a 3 amp scale, which tells you from 0 to 3 is the whole deflection of the needle. Then it will say something like 500 milliamps. And if you can see that it's lower than half an amp, then you connect it to the 500. If it's reading 1,2, you don't change the terminals. So that's just a little bit of a practical, some hints for practical. Now, what we want is the reading on the ammeter. What does current depend on? Current, we know, here we're not given any information about Q over T. Nothing is like that. But we know R is equal to V over I. And we also know that it doesn't matter in a series circuit where we put the ammeter. If I'd put the ammeter over here, for example, if I'd chosen to put the ammeter over there, it would read the same as if I put the ammeter over there, or over there, or over there, or over there, or in fact between those cells. At all points in a series circuit, the current is constant. It doesn't change. So we need to be aware of that. So we're looking for total current. So in this circuit, because it's series, we want I total. And if we want I total, then we also want to find V total, and we must work with V total, and we must work with R total. It's not just one little bit. So I'm breaking down the problem into more than one part. The first thing I'm going to do is I want to find I total. So I'm going to try and calculate V total first of all, and then next I'm going to calculate R total, and then I will use Ohm's law. So I've worked a little bit backwards. Let's hope that we can do it in the space. So the first thing I'm going to say, V total. Well, we knew that we got 1,4 volt cells, and there were 4 of them. So V total, in this case, is 4 times 1,4, and that gives me 6 volts. Check it on the calculator. Where's my calculator? There it is. 1,5 times 4 equals 6. Got it. So we were right. Now, guys, in this case, there was no mention of internal resistance. The total potential that a battery can deliver, that it can produce, is called the EMF. And in most cases, that isn't actually the amount of potential that it does produce in the external circuit. Some of it, of that energy, is used up inside the battery itself, in getting the charges from the negative terminal back to the positive terminal. And so we are not going to specify and deal with EMF tonight and internal resistance. We're going to take EMF as the maximum, and we're going to use that maximum value as being available in the external circuit. We're going to say the internal resistance is a minimal, is negligible. We can ignore it. Okay. So the next part of the circuit, or the problem, was we've got V total. Now let's work out what R total is. Now R total, all the resistors are in series. So we can just add them up. R1 plus R2 plus R3. And if we do that, it's 2 plus 4 plus 6, and that gives me 12 ohms. And then the final step is to find the current. We're going to say I total is equal to V total. Sorry, let's change that around. I want to make a point here. We always use the equation as given on the data sheet. And we always say, if this is total, that's total, that's total. And we're going to substitute into that. So we're going to say 12 is equal to 6 volts divided by I total. And now I change the subject of the formula, and if I do that, I can say therefore I is equal to 6 divided by 12, which is 0,5 amps. Put the reading in. Now, people, the reason that we take the formula and we substitute like that, and we don't try and change the subject of the formula, the marks are given for writing down the formula from the data sheet. Secondly, marks are given for substitution. If you don't write down the right formula, you're losing a mark. If you then use the wrong formula and you substitute, you don't get any marks for substitution. So you get very little marks overall. So please write down the correct formula, substitute, and then change. Okay, that's just the way the examiner wants it. Next question. It says, now, what would the reading of the voltmeter be when connected across the 4 ohm resistor? So now we've got a voltmeter, and we're going to take this voltmeter, I'm going to use a different color, and we're going to connect it across the 4 ohm resistor. And we're going to use Ohm's law to do this. we want to get the reading of the voltmeter. We've got the current. How do we have the current? The current in a series circuit is the same everywhere, even through the 4 ohm resistor, even through the 6 ohm resistor. The charges are not slowing down. Please don't think that they're slowing down, because no, they're not. They've got these energy packs that make them go the same speed through the resistance. Okay, so we want to work that out. Listen to what I said. R is equal to V over I. We want the resistor. What resistor was it? The 4 ohm resistor. We want the potential difference across the 4 ohm resistor, and we want the current through the 4 ohm resistor. Now, if we do that, we can start to substitute. What's the resistance of the 4 ohm resistor? Yeah, that's 4. What's the potential difference? We don't know. What's the current? Well, we do know. We've just worked it out. 0,5. So if I do that, I can now say, therefore, the V through the 4 ohm, or across the 4 ohm resistor, is equal to 0,5 multiplied by 4. Put the things in brackets so that there's no mistaking, and we can obviously see that is 2 volts. So remember what was available. What was the total? There was 6 volts available. 6 volts was available for that whole circuit. 2 volts has been used up in the 4 ohm resistor. Do you see a pattern there? Hope you do, because what do you think if that was, what was it? What do we work it out to? 2 volts. Do we say 2 volts? Then I think, and I think you need to go and show this, that we'd have 1 volt there, and we'll have 3 volts there. Now, if that's correct, 1 plus 3 volts is 4 volts, and 4 volts from this one, from 2 volts, will give us the total, which was our total, which was 6 volts, which is available. And that's the reason I can say that, is it because it's in a proportion. The bigger potential, the bigger resistor, higher potential. Smaller resistor, lower potential. Please make sure that you can follow that logic of resistors and the ratio of the resistors. Fortunately, we haven't got time to finish the last part of that question just yet, but let's take a break. AB's got some news for us.
Thank you so much, and I'll tell you those news after the break, because I think you guys deserve some break also, but there's a challenge question during this break. So after the break, I'll be telling you more about more competitions and more giveaways, so stay tuned. Welcome back, awesome mindsetters. Now the great news are we have another competition. It is the South African Water Game competition, hashtag SA Water Game. All you need to do is to register and play on www.watergame.co.za. You stand a chance of winning some awesome, cool prizes, such as a bursary worth 15,000 Rand per year at the University of KwaZulu-Natal. But more details are on facebook.com/learnextra. So guys, it's a serious game competition. You're playing, but you're learning more about water at the same time, because we like educating you guys while you are learning. John?
Absolutely, and I hope you're having fun this afternoon too. Remember, water is very important, and playing the water game, it's an online computer game. Make sure that you've got time, because it can become addictive. You can go through the whole game in less than 30 minutes, but then you want to beat your score. And remember, you don't just have to stop playing after one go. You can play again and see what decisions you can make to improve the environment. The person that gets the best score overall is going to be that lucky winner of all that cash. Okay, so let's go back to our question. Question number 2 now says, the original circuit, the one that we drew, has been disconnected. And then it's reconnected with the 4 ohm and the 6 ohm resistor. They're in parallel now, while the 2 ohm remains in series to the battery. So what I've done is I've quickly drawn the new circuit diagram, because I like to work with a circuit diagram. Just remind you that in the original question, they told you that each of these cells was 1,5 volts, and there were 4 of them. So that's why we know that 1,5 times 4 is going to give you a 6 volt battery. Okay. Each of the cells was 1,5, and we've got 4 of them. That's the positive terminal. That's the negative terminal. 1, there's 2, there's 3, there's 4. So we've all sorted with that. We're just answering somebody's question about where the 1,5 came from. We've got it now. Now, we've connected the 6 ohm and the 4 ohm in a parallel branch. The ammeter is still connected in the main circuit, and the 2 ohm is in series. What it now says, what would the reading of a voltmeter be when it's connected across the 4 ohm resistor in the new circuit? Remember, we connected the voltmeter in the previous one, and we found that it had a certain reading. We just did that, and we found that over here, the voltmeter had a reading of 2 volts. What we want to do is now find out what the reading of the voltmeter is here. So guys, here we've got to do some calculations, and I'm going to run through these very quickly. What we've got to recognize in parallel, your reading across a branch in parallel is the same as if it's across the whole circuit, the whole branch, or across any of the resistors. Potential difference across parallel branches is the same. So what I'm going to do is I'm going to start by working out the resistance of that parallel branch. And I'm told that the equivalent resistance, or the resistance of the branch in parallel, is 1 over R plus R1 plus 1 over R2. And I'm now going to substitute that in on the side. I get 1 over 6 plus 1 over 4. And I can look for the common denominator. 6 and 4 is going to be 12. 6 goes into 12 twice. And 4 goes into 12 3 times. And that gives me 5 over 12. Is that my answer? I hope you're saying no, because that was 1 over. We want R parallel, or R equivalent. And that's going to be 12 over 5. Flip it up and check it. And that will give you 2,4 ohms. Don't leave it as a fraction. Make sure you work it out. So we now know the equivalent resistance. If we had to take that whole resistor, that branch away, and replace it with a single one, we would be replacing it with a 2,4 ohm resistor. Now, I next need to work out what the total current is into that parallel section. I'm not so worried about the current through that part, because that might be a little bit tricky for me to do just yet. So I'm going to say, let's work out the total resistance. Total resistance is equal to, the first thing I can say, it's the series bit plus the parallel bit. We've worked out the parallel bit. The series bit was 2, plus the parallel bit was 2,4. So the total resistance is 4,4 ohms. So I know what the total potential difference is. I know that was 6 volts. So I can work out what the current is, the total current. Total current, I'm going to change my rule just very quickly, just because we're running out of time, and say, let's just change it to V total over R total. And we're going to say 6 volts divided by 4,4 gives us an answer using the calculator. 6 divided by 4,4 equals, this is my current, 1,36 amps. So now, what I've got to recognize is into this parallel section comes 1,3, what was it? 1,36 amps. And out of that section, out of this section comes it's over here. It's not in this place here. It's at 1,36 is where they are there. It does divide, and more current goes through the lower part. More current goes through there. Current comes through here, joins back, and I've again got 1,36 amps on that side. Now guys, what you've got to recognize is you want to do this simply. you want to get the potential difference across the 4 ohm. The way to do it is to recognize the potential difference across the 4 ohm is the same as the potential difference across the parallel. And the potential difference across the parallel is the current coming into the parallel times the resistance of the parallel. And that, if I've not made a mistake, is 1,36 times 2,4. And let's do it on the calculator so we get it correct. 1,36 times 2,4, and that will give me an answer of 3,264. I'm going to write it as 3,26 volts. And there we go. We've solved that question. Let's move on to the challenge question now, because this one has got some more challenges for us and tricks for us. So the first thing that I'm going to do is I'm going to analyze this diagram very carefully. I'm going to say to myself, I know the ammeter is the same reading, so current is the same, of whether S1 and 2 are either both open or both closed. So now, if I know at the moment they're both open, so let's follow the current through. The current can go through this part, it can go through that one, it can go there, it can go there, it can go there, it can go there. I know the potential difference, and so therefore I can work out the current. They're both open at the moment, and there's no problem with that. So I'm going to work out the current. I know the total potential difference, V total, is 4,5. Do I know R total? No, I'm going to work it out. If I recognize that circuit, it's a series circuit, so R total is equal to R1 plus R2 plus R3. And I'm going to add all of those together, and I'm going to say to myself, what have I got? I've got 6 ohms, followed by a 1 ohm, followed by a 2 ohm. And if I add that together, then I'm going to say that R total is 9 ohms. 9 ohms is my resistance of the circuit. So what is the reading on the ammeter? Not difficult. Use Ohm's law. Ohm's law says R is equal to R total is equal to V total over I total. Make sure you're always using the same ones. So we therefore don't try and get smart and put them onto one line. We're going to now substitute. We know 9 ohms is equal to, what was the V total? It was given. There's no internal resistance, so it's 4,5 divided by I total. So therefore, we can change the subject of the formula and say I total is equal to 4,5 divided by 9, and if I'm not mistaken, that should be a half. But let's use the calculator to make sure. We're going to say 4,5 divided by 9, and we're going to get a half. And so we know that the current is half an amp. That was the total current. We also know that the current passing through when the circuit is closed. Okay, so now we're going to close the circuit, and we're going to say in the closed circuit, because this is the only thing that we can work out. In the closed circuit, let's close the circuits. I'm going to put a line there. You know what? I'm going to do it as a straight line because I want to keep it in. I'm going to put that line there and that line there. So now let's examine our circuit very quickly. Let's examine our circuit. What have we got? From the positive terminal, we've got something divides. It divides over here. So we're going to have a split in the current, and some of the current goes this way, and some of the current goes this way. Okay? Now, the question is, are you going to get any current going through this part here? No, you're not. So that's a short circuit because all the current will go through the simplest way and it will come back to there. So I'm just going to look at that circuit. So really what I've got is a 6 ohm resistor and an unknown resistor connected to a 2 ohm resistor, and I know that the current through this part of the circuit is 0.5 ohms. 0.5 amps. Through that part is 0.5 amps. Now, this might seem a little tricky to you, but it really isn't. What we've got to do is we've got to make sure that we can work out the total resistance. We work out the total current first of all, total resistance, and then the total current. So we do exactly the same thing as we've done before, and just because it's easier, I'm going to erase some detail here. So we still know that the total potential is 4.5, but now the resistances are different. Have a look at what we've got. We've got an R and we've got a 6, and we've got a 2 ohm, and we don't know too much else. I don't know whether this is possible now that I'm looking at it, and so I'm just going to set something up and hopefully it will work. We know that we've got total current is what we need to find, and we're going to find total resistance. We're going to put in total resistance, and we're going to say total resistance is made up of a resistor in series and then one in parallel. There's the parallel branch. And in this case, because I don't know that R value, I'm going to say let R equal X for the moment. I'm now going to work through this and see if we can get a value. Let's hope we can. So R parallel is going to be 1 over X plus 1 over 6. And if we do this, you're going to get 6x over X goes into that 6 times, 6 goes into that X times, and we then must switch over the denominator. Remember that was 1 over R, so R parallel is going to be 6x over 6 plus x. Now, that looks very scary because then the total becomes this resistor here, 2 ohms must be added to it, so it's 2 ohms plus 6x over 6 plus x, and if we break this apart, we're going to say 6 plus x, common denominator, it will go 2 times 6 is 12 plus 2x plus 6x, and it's really getting messy, but we're getting a 12 plus 8x, and that's all over 6 plus x. Now, that's the total resistance. We're needing to find a little bit more information. And hopefully we're going to get it now. Because what we know is the total potential is 4 volts. We know the total potential is 4 volts. So let's get it here. Total potential 4 volts, 4.5 volts. And the current, not the total current, but the current through here is going to be 0.5. Now that's problematic because we don't know what the other one is, so we're going to need to have a think about this. It's going to be in a ratio with that. There's a way of getting a solution. I'll see if I can post that on Facebook a little later. Okay.
Thank you so much.
So, but remember, if you get stuck, at least do some working. Like I've got stuck and I've just lost my train of thought. Okay.
And well done to everybody that gave the challenge question a try, and thank you for your answers. Really appreciate it, guys. It shows that you're concentrating and you focus and you are learning with us. But now, before we end the show, let me just announce last week's winner for this awesome Casio calculator, and it goes to Nyoza Simbine. Congratulations to you, Nyoza Simbine. This awesome Casio calculator is coming your way, guys. We love you and appreciate you guys for joining us today. From me, AB, and John, we're leaving you in peace.